Okay, Wiz, I've heard about this attention thing for a while now. And I heard it's all we need, but flash attention is coming up in the game and is maybe a new contender for all we need, isn't it?
Yeah, absolutely. I mean, flash attention is attention, but in a flash, it's just faster.
It
That's
is.
it.
And so if we're going to go and we're going to go ahead and calculate attention, is there really ever a reason anymore to do it naively like we did in the old days, or should we just pick up something like a flash attention or a flash attention 2 off the shelf?
Yeah, if your architecture is compatible with flash attention, you should just be using it. Period.
And it'll be done in a flash. Huh. Like this intro, let's go. All right, we'll see you back in a bit, Wiz, to discuss some of the many interesting aspects of hardware and software interfaces that we'll get into today. Thanks, Wiz, and welcome everybody. Today we're going to talk about flash attention. We're going to talk about attention, flash attention, flash attention 2, and we're also going to talk about flash attention 3 and tell you why you probably don't need to use it. This is a sort of wide-ranging discussion because we have to go into quite a few hardware details. So if that's not something that you're particularly comfortable with yet, this is going to be a great intro session for you. If you have questions along the way, go ahead and throw them into the Slido link that will drop into the YouTube chat now. And while we're having discussions, you can also feel free to pop into the YouTube live chat and we'll check it out, see if we can kind of keep the discussion rolling with you guys. With that, I'd like to go ahead and kick it off, get into FA2 and figure out why this is really a next level way to calculate attention. Now, of course, we've heard about attention. And as we align ourselves to the session today, we do want to do a slight review of attention, but it's going to be the kind of review that we do. We're sort of, kind of like, yeah, you know about attention, right? And that is just because it's quite difficult to go down to the computation level of specific attention calculations without taking a ridiculous amount of time. So we'll kind of cover the core aspects of what we need to know to understand flash attention, and then we'll focus more in on what's going on and the kind of tips and tricks that they're using, the techniques that they're leveraging to make everything faster, and in what ways we mean faster. We'll also talk about FA2 and FA3, and you'll see kind of the natural progression. I mean, since Attention is All You Need came out, we've been working on this kind of get this thing right for the last 6-7 years now. So there's been a lot of interesting, cool stuff going on. And we're starting to run into some limits that are really at the hardware level of GPUs. So this will be a fun one today. We're going to use Phi 3.5 mini instruct just because it's a small, easy to leverage model. You guys should be able to run it as well. And Wiz will walk us through that at the end to show what the difference is if we pull a model off the shelf versus if we go ahead and do inference with flash attention. First, let's go ahead and review attention before we get into everything else. We'll come back to this meme right here. And by the end, I think you have a pretty good idea of what's going on and what the bottlenecks and limitations are of compute today. All right, so when we talk about attention, we need to talk about the fact that we're looking at a single word and we're attending to that word token, right? But we can sort of say word for conceptual understanding. And when we look at that specific word, we can look at all the other words around it and we can say, what is the meaning of this word? What am I learning from my context around this word? That's sort of at the sentence level. Now, if you think about sort of a few levels higher, kind of at the world level, you can kind of think about what the GPT style transformer is doing with multi-headed attention, with this great line from the Attention is All You Need paper. Multi-head attention allows the model to jointly attend to different representation subspaces at different positions. Okay, what do we sort of to make of that? Well, you can sort of think of the different attention heads that are in each attention layer as paying attention to something different in the data that we're feeding in. And so if you consider the data is kind of this representation of the world, you can imagine that each attention head is kind of trying to look at some slightly different aspect of the world. This is especially true not just within an attention layer, but as we go from attention block to attention block. Typically, we're going to see many blocks that have attention layers. In this case, we have in this diagram just 12 of these blocks. So as we go from block to block, or as we look across attention heads, we're sort of paying attention to different things. The analogy here that's good is sort of the university has different departments. Each department is going to pay attention to maybe the same phenomena, but they're going to look at it from a slightly different angle. And this is useful because when we can look at it from all the angles, then we've got a pretty good understanding of what's really going on. But high-level conceptual stuff aside, it's more important today to talk about the calculations. And we're not going to go super deep into this, but we're going to go deep enough that we can talk about flash attention. An attention function is described as mapping a query and set of key value pairs to an output where the query keys, values, and output are all vectors. The output is computed as a weighted sum of the values where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. Gee, it sounds like a lot of calculations. And in fact, it is a lot of calculations. This here is sort of showing one single word and how we would do kind of some attention calculations for it. Now you see a number of steps here. We've got the embedding representation, we've got query keys and values, and we've got sort of this multiplication, this division, we've got this softmax operation, and then we've got this sum at the end. So there's a lot of, even just with a very, very simple example, a lot of number crunching going on. Now, generally, we're going to be using this scaled dot product attention. The calculation is shown here. Importantly, the softmax is around this whole thing, and then we have this sort of Q, K transpose, this vector representation divided by this D sub K times V. So we have query, keys, values, and then this dimension here. Okay, so this, again, is just for like one word. We have lots more than that. Typically, we're going to be doing this not on a single set of query keys and values, but on many queries. And we're going to do this in matrix form. So this is sort of the matrix representation of this equation. And you know, you can visualize this in some way. Jay Alamar's Illustrated Transformer does a wonderful job of breaking this down. So we can kind of start thinking about how these are really just matrix operations going down. And as the sequences get longer, the matrix operations get bigger. As the neural networks get bigger, the matrix operations get bigger. Now, it's also important to understand as we grow our model sizes, GPT models, for instance, some of the early ones were like 12 blocks with many different attention heads in each block. So that block, that layer that we're calculating attention is calculating this sort of attention that we saw, the scaled dot product attention, and it's calculating it a number of times for each head, and that's all within a single layer. So we're doing this again a bunch of times for each head, all within a single layer, but there are many layers. Typically, we'll see something like a 12-layer, 12 block in some of these older models. This is the original GPT. as we progressed 2018 into 2019, GPT-2, we saw, okay, now we're dealing with 48 layers of multi-headed attention. Remember, so what we're talking about here is we're talking about how each decoder block, if we look at the GPT-2 extra large, has this setup where we have many heads in each block, many attention calculations, and many blocks, 48 of them in this case. Of course, we continue on, right? GPT-3, 2020, language models are few-shot learners, 96 layers, 96 heads. And we continue on. What do we see today? Well, we see that Llama 3.1405B is now in this ballpark, 126 layers, 128 heads. So all of a sudden, we have this explosion. There's just lots of calculations, basically, okay? But can we do them in a flash? We can. Now, this is where it gets interesting. Let's take a look at what the paper says. This is from May 2022. Transformers are slow and memory hungry on long sequences, since the time and memory complexity of self-attention are quadratic in sequence length. So we get this keyword time and memory complexity, and quadratic, it doesn't scale linearly. It scales to the square. It scales quadratically. Typically, we're dealing with square matrices here. And that is never quite good for minimizing compute and optimizing for speed. When we talk about complexity, we're just talking about how scalable this thing is. We want to lower the time and memory complexity. Specifically, when we talk about what this paper talks about and what we'll get into today, when we talk about I/O complexity, when we talk about input-output complexity, we talk about the number of reads and writes that we have to do. We want to minimize these because despite having to do all these calculations, we always want to actually do more of them. We keep scaling. We're going to scale the number of model parameters. We're going to scale the time we train. We're going to scale the amount of data that we use to train. So we have to always be working to reduce this kind of complexity. And the paper goes on to say that, yeah, people have been trying these approximation methods, this type of surrogate modeling technique. And it's like, it's all right. But there's this real trade-off because you're giving up accuracy to reduce the complexity. And maybe that's not so good if you want your LLMs to be performant and efficient. And oftentimes, maybe they're actually not really speeding up inference all that much. So the FlashAttention paper points out making attention algorithms I/O aware is the key. Now, this is sort of reminiscent of things that we've talked about previously on this channel. Activation aware quantization, for instance, this sort of awareness of what's really going on at a very detailed level is where we start to get to with some of these more state-of-the-art techniques. Check this out. Accounting for levels for reads and writes between levels of GPU memory. Okay, what does this mean? Well, in short, it means that shuffling memory around is quite annoying, okay? That's what it means. Let's take a look at the inside of a GPU real quick so we can try to understand what we're exactly every day I'm shuffling. Okay, let's take a look here. See if we can get this to work. Shout out to Branch Education.
Perhaps some of the most important components, aside from the GPU, are the 24 gigabytes of graphics memory chips, which are technically called GDDR6X.
Okay. Did you catch that? So these graphics memory chips, these are connected right to the GPU. And these are pretty legit. They're pretty fast because they're like right there next to the GPU. We don't have to shuffle things once we get stuff there. Okay, so let's take a look at what the paper tells us is the solution. Flash attention, an IO-aware exact attention algorithm. That sounds pretty good. Not approximate. That uses tiling to reduce the number of memory reads or writes between 1. GPU high bandwidth memory or HBM and GPU on-chip SRAM, the kind we just took a look at. It's on the chip. Now, when we talk about high bandwidth memory, we're talking about, if you look at an A100, you can kind of get this 1.5 to 2 terabytes per second. Yeah, that's pretty good. Sounds like a lot. However, this is not attached. It's not directly attached to the processor. Whereas the on-chip SRAM that we just took a look at, that's more of like 10x speed up on these A100s, more like 19 terabytes a second. That is directly attached to the processor. And so the kind of analogy here, the classic analogy that's sort of obvious to all of us that use computers, is like the HBM is kind of like our hard drive, and the GPU on-chip SRAM is kind of like our RAM. And so we don't want to have to be moving stuff from the hard drive to the RAM if we want to be super fast. We can sort of visualize that again here in a real quick visualization that I'd like to just kind of show you here, where we could kind of see that if we look at kind of this solid state drive, of course, shown here is that we've got kind of graphics that we're trying to process with a graphics processing unit. You kind of have to shuffle, you kind of have to move things from the solid state drive into the graphics memory chip. If you think about graphics, you're sort of moving parts of that 3D world into it as you need it to sort of complete the scene. Of course, that's not what we're doing, even though it is. You see, GPUs were never really created with this kind of attention calculation in mind at all. I mean, they're graphics processing units. Hence, the stuff we start to see on the market today from companies like Grok building learning or language processing units. And look at that architecture. It looks like there's a lot of different stuff on it. And indeed there is. This one looks a little bit more straightforward, a little bit more streamlined. Interesting. There are other competitors in this space today. People like Samba Nova, Cerebras, and they're all competing. You can kind of see here, data center footprint comparison for Llama 3.170B inference. This is what people talk about when they talk about sort of matching the hardware to the software. Everybody sort of understands now that the bottleneck today is the memory. The bottleneck is the shuffling. The bottleneck is the moving stuff from HBM to SRAM. So I want to bring Wiz up and have a little chat here. Okay, so isn't it true, Wiz, that it used to be that we could not compute as fast and we had plenty of memory, but today we actually can compute super fast. We just need more memory. Is that right?
I mean, yes. So definitely that is the a way to characterize it. I would think of it more like what we're doing is we're computing so much stuff, right? Every time we do an iteration or a single auto-regressive step of inference, right? We have to move through some, 8 billion parameters. So it's the issue we're having now is because there's so much stuff to shuffle around, right? Our processor is able to do the work, right, faster than we can feed it more work. And so we run into this issue where we become memory bound on these kinds of applications because the effort, let's say, that it takes to compute this is relatively low. There's just many of it, especially as we get into 405 billion parameter models, where there's so much shuffling of data that needs to occur that and the operations the GPU are doing, it is so optimized for that we wind up in this situation where yes, the speed at which we can shuffle these parameters around and get our the segments of our weight matrix into our processor is much slower than the actual time it takes to do the computation. Yeah.
So, I guess sort of the question is like, what exactly is being shuffled? You said segments of the weight matrix here.
Yeah.
So, I got to imagine that when you get to 405 billion, it's just too freaking big to put all into one GPU at once, right? And this is where we get into the clusters of many GPUs and all this kind of stuff too. But what exactly is being shuffled? What's the easiest way to think about it?
Yeah, there's two things in flash attention that are important. Number one, actual matmuls you can just do on little chunks of the weight matrix. This is the beauty of
matrix multiplications.
That's right.
Matmuls. Okay.
Matmuls. So matrix multiplications, you can just do those like piecewise. You don't have to do them all at once. You've never had to. Humans don't do them all at once. The computer doesn't need to do them all at once. There you go.
I remember in your algebra class, didn't do them all at once.
Didn't do them all at once.
One at a time, baby. That's right.
And so we could just chunk the matrix really easily. One part that's a little bit harder, right? And this is Flash Attention's come up with some novel solutions for this, is the softmax step of the attention mechanism. But we can still do that piecemeal, right? As long as we keep in memory in the result of each little chunk, the running tally, right, of these little chunks, and then we broadcast and share that information if we move beyond one single GPU, etc. Right? The way that we modify this as we scale to more GPUs is kind of samey, right? We're able to then just, at the end of the day, check everybody's score, update, away we go. It's actually because, the thing we're doing are matrix multiplications, and because we can change softmax from this all at once to an incremental operation, that we're able to even consider these kinds of optimization, or this level of optimization. If those things weren't true, if we had to have the whole matrix in memory at the same time, right?
Yeah.
It would be impossible to pursue these avenues.
That's super interesting. Okay. And so it's sort of the scope and scale of these models is causing this memory bound issue.
They're just so big.
They're okay. They just keep going. Burr. Okay. All right, Wiz. Well, we're going to have you back in just a bit to keep the discussion rolling. So, I think what we want to take away from this is that memory access is slower than computation, and that's the bottleneck. Okay. So now there's some interesting things happening within Flash Attention. One of those things is they wrote some kernels, and the kernel is simply a GPU program that fuses kernel fusion, kind of fuses some calculations together. You can kind of think of this, if we go back to the attention calculation and bring in this matmul idea we heard from Wiz, you could ask yourself, like, how many reads and writes are needed to do the calculation for scaled dot product attention one time in one head in one layer. And so we have to sort of read in Q and K. We have to then write the matmul output. We've got to then read in the matmul, write the scale output, and so on here, just for sort of one of these. And this seems a little bit inefficient. Now, there's also other interesting ideas like caching K and V values. Oftentimes, those don't need to necessarily be calculated over and over if you're going to get the same result. But putting that to the side here, if we can, let's say, fuse all of these calculations together so that we're not doing a bunch of individual distinct ones, that would make stuff run a lot faster. And this is something we're doing all the time. This is something that you'll see in so many different research papers and frameworks that come out, kernel fusion and micro optimization. So let's take a look at the main figure from the paper. 26 minutes in, let's check it out. We can start to kind of understand this. Let's take a tour and let's avoid the middle here at first. We see the left-hand side here. Every day I'm shuffling. We have the GPU, high bandwidth memory. This is sort of that 1.5 terabytes a second. We also have the GPU SRAM, the on-chip SRAM. And you can kind of see this hierarchy of speed and memory size. And this is sort of consistent with our discussion we've been having so far. Now you'll also come over here to the right and you'll see, like, look how long it takes to just simply do this kind of calculation on like a GPT-2 versus if you have more of a fused kernel. And a great example here is like, let's say you wanted to add 5 plus 5 plus 5 plus 5 plus 5. That's like 5 operations. What's an easier way to do that? Right? 5 times 5, right? And then like all of a sudden you're done super fast. And so we're looking for things like this, sort of after we have the end-to-end perspective of the calculation that needs to be done, we're seeing if we can collapse it down into more of a one-shot calculation. Now, this specific looping mechanism, a little bit harder, and we're not going to go into great depth on this. Flash attention loops through blocks of the K and V matrices and loads them to fast on-chip SRAM. In each block, flash attention loops over blocks of Q matrix, blue arrows. That's the blue arrows. Boom and boom. Loading them into SRAM and writing the output of the attention computation back to HBM. So it's doing a special thing to make it a little bit faster. All right, so 7.6x speed up. That sounds pretty dope. Pretty sick. All right. So that's flash attention. 2022, 7.6. Nice. Of course, the story doesn't end there. In 2023, FA2 came out. In 2024, FA3 came out. What does FA2 say? Well, FA2 says, we observe that the inefficiency is due to suboptimal work partitioning between, get this, different thread blocks and warps on the GPU, causing either low occupancy or unnecessary shared memory read writes. Ooh, that sounds pretty deep because it is pretty deep. So low occupancy or unnecessary shared memory read writes. On the warps, okay, so get this. You can visualize a warp like this. There's the GPU, and then there's the processing cores, and then there's the graphics processing clusters, and then there's the streaming multiprocessors, and underneath those, inside of those, you find the warps. And then in the warps, that's where your CUDA architecture, CUDA chips are. Okay, so like we are deep in the game on optimizing when we're at the warp level. All right, that's the first thing just to keep in mind here. And it turns out that if we just sort of pull FA2 off the shelf, works pretty good. Works pretty good. Now, I just want to loop in this last piece before we have our next little discussion. And I want to tell you about FA3 here. So FA3 is actually going to be from July 2024, and FA3 here is based on this other type of architecture. It's based on these Hopper GPUs. That's like a new kind of GPU. And in that context, they're then exploiting this asynchrony of the tensor cores to now, obviously, you know, many of you, even myself included, are a little bit lost at this point. But we can start to see some shadows of things that we really can connect with. Overlap overall computation and data movement via warp specialization. Okay. Interleave blockwise matmul and softmax operations. All right. Okay. Yeah, that's making sense. And block quantization and incoherent processing that leverages hardware support for FP low precision. If you followed our channel and have learned about quantization in the past, we can start to get some intuition there as well. Now, the Hopper GPU is literally just a new GPU architecture named after Grace Hopper, an old school legend in the computation space. Okay, so Wiz, I need your help with this. There's a lot of words being thrown at us now. Okay, thread blocks, warps, Hopper GPUs. What do you make of all of this? And then what should people really care about here if they're trying to build, ship, and share production LLM applications?
None of it. So you know, it's the truth that this is an extremely amazing, innovation. We're doing a lot of work in this space, but as for building, like the only kind of thing you need to worry about is if you're not using Grace Hopper GPUs, so you're not using the Hopper architecture, then you should just use FA2, right? So that's FlashAttention-2. If you are, you might find that you have performance increases as you go to FA3. Like that's it, right? If you're building LLMs from an endpoint that's already stood up by your MLOps team or your LLMOps team, you don't even have to worry about that. You just hit the endpoint, right? So, but knowing about this stuff, exploring this stuff, right, adds a lot of context and understanding as to how this machine works under the hood, which can be useful if you're going to be training models, if you're going to be thinking about how to most effectively deliver models, that are not wasting your time, right? If you're thinking about the user experience of your model, using something like FA2 is going to just be better than not. But yeah, ultimately, thread blocks, warps, we don't got to worry about that stuff.
Okay.
Yeah.
We've got some cool. We don't have to worry about that stuff. Okay, so we'll see when we do have to worry about it, and we'll follow the trail of FA2, FA3. I mean, I guess the other thing that's interesting here is like, so NVIDIA is coming out with this new architecture, the Hopper GPU. We see Grok and Samba Nova and Cerebras coming out. Like, this is because it's a graphics processing unit, right? And you have these things like ray tracing, and you have this other graphics stuff that like we just literally don't need to run attention calculations and LLMs, right? Like that's the whole thing.
Yeah, I mean, the current consumer grade GPUs come with a lot of extra baggage that's totally unnecessary, right? So having these data center GPUs that are without that baggage, right? is extremely effective because it just cuts down the amount of space that we're taking up on the chip with stuff that doesn't matter, and reutilizing that space for things that make LLM go burr. So it's all about the usage of the software dictating how the hardware goes, and then how the hardware improves dictating how we can make software optimizations, and back and forth. This is why Flash Attention is a great example, right, of how we progress through the hardware software cycle, right? FA2 leverages new features. FA3 leverages new features. This is something that we can get because the industry is responding to the demands of people who are building large inference focused services versus just like trying to render stuff real good.
That's right. That's right. Yeah. Okay. So we've got a couple questions in the chat. I want to. Looks like Matul asks, like, how is softmax computed in chunks? I wonder. I know we did give an answer here, but you mentioned softmax as being a little bit harder to calculate. I wonder if we can just double click in on that here, then maybe attention. Why is that, and what implications does it have for computation?
Yeah, I mean, what it comes down to is the fact that matrix multiplication is it's trivial, right, to partition. We have to think more about softmax. Softmax is something that we think about as being all at once, right? But it doesn't have to be. We can compute it incrementally as long as we keep track of what's been computed so far. That keeping track does take up some memory, does introduce some latency, but it's much faster than trying to do it all at once anyway, so there you go. But the idea is the same way you can think about like an average, right? You can keep adding new numbers to an average and keep recomputing the average as long as you know what you had before and what you have next. You just have to
because softmax, like, you have to look at all the numbers before you can decide which one's the max, even if it's soft. It doesn't have to be a hard one.
That's right.
Okay, so then another quick question here from Black Current 07. What's up, Black Current? How about the Blackwell GPUs coming out? What's up with those? Should we be paying attention to Blackwell?
No. I mean, people like FlashAttention-2, paper writers should be taking account of that. That's it. As for builders, we should use them if they're fast, especially if they're very good at inference, especially if they're good at quantized inference. But we will be leveraging the research work as opposed to, worrying about implementing these ourselves. Unless you're into this stuff, then heck yeah. Get yourself access to a Blackwell GPU and start optimizing. They're not super cheap right now, but, there you go.
Love it. Love it. Okay, so that's about time for you to jump in and show us how to benchmark the model we've chosen today, Phi 3.5 Mini Instruct, and show us, is it really happening in a Flash when we use it? So I'll go ahead and hand it off to you, my friend. Wiz?
Yes.
Take it away.
This is the best. Okay, so look at this. We got a notebook. We're not going to go into how to implement FlashAttention-2 because it's not. We can look at the code and be bewildered by how beautiful it is. But that's all we can do. As far as the actual implementation in code, you can see here FlashAttention-2. We've got a lot going on, right? They're recreating some layers depending on what models you're using. We have the idea of a Triton inference optimization, package. Long and short of it is, there's a lot of code that does very cool stuff, but we don't care because the way we use it is we import FlashAttention. Okay, you'll notice in the collab that we downgrade to 2.4 as opposed to 2.5. You technically don't need to do this, but if you don't do this, FlashAttention will take hours to install. So please do this. There you go. Okay, so we downgrade to 2.4, and then we can install FlashAttention and Accelerate. The rest of the things are provided to us in collab by default. Very cool. We have a wall of imports. We have our old favorite friends from Transformers library, auto model for causal LLM and auto tokenizer. And then for our helper functions, we have a bunch. We're going to use phi 3.5 mini instruct. Phi 3.5 mini instruct is a very small model from our friends at Microsoft. It's, look at this, 3.82 billion parameters, so tiny. The idea here is that we want to run this attention mechanism on a variety of sequences. So we want to run it from very short sequences to very long sequences so that we can really understand why flash attention is great. In order to do that without quantizing the model and just kind of winding up being like, look, quantize model fast, which we already kind of know, we're doing it this way. We just load the model straight up raw, and we can do that since it's Phi 3.4 mini. You'll also notice that I'm on a A100 instance for this. You do need to use that instance. If you want to use a smaller instance, you'll have to reduce the sequence length. That's just the way it goes with GPU memory. Remember what Greg was talking about? We have HBM, high bandwidth memory. It's big and slow. We do need to put the model weight somewhere, and when we do the computation, we still need to load the weight matrices into memory. This does mean when we have really long sequences, we're going to have a lot of memory consumption, and so even though we're using flash attention, right, it's not actually impacting the straight up memory usage, but that's dope. Okay, clear memory clears memory. There you go. Run inference. You guessed it, runs inference. Then we have our benchmark sequence. So we convert our inputs into IDs, so we tokenize them. We pre-tokenize them, very, very importantly. And then we create an attention mask. We do not need a attention mask because we're not using any padding. But it is just helpful to very strictly ensure that we're not accidentally churning through a bunch of padding tokens and therefore our data is bad. Okay, so that's why we use attention mask. Then we have our warm-up. So basically we want to warm up so that the first generation can literally be slower as the model goes through that first process of loading data into memory. So what we do is we do a couple passes. We don't count them for the trial, and then we start the trial once the model's warmed up. We time it using our time library, and then we return our trial mean and standard deviation. We are running trials, so 10 trials for each sequence length, for each implementation. That's it. Pre-downloading the model, we just do this so that's not in the first step. We could just do it in the first step. It doesn't actually impact the timing, but it's cleaner this way. I like it better. That's why we did it. Okay, so we have to download the actual model weights, right, before we do anything else. Same with the tokenizer, we just get her done. And then we create the experiment list. So we're going to do from 512 to 6656 tokens. This is to show a variety of sequence lengths. As I said, we are limited by GPU memory here, right? So flash attention doesn't really do anything in terms of saving us GPU memory. So we can't do like 128K in the 40 gig A100. So that's why we're stopping at 6656, but it's still it's enough sequence for us to really feel the impact of flash attention. We're doing increments of 512, so we have many points, so our graph looks like a beautiful little curve. And then, of course, we have our two implementations of none and FlashAttention-2. Then we're going to create exact length sequences. Since we have our tokenizer, we can create sequences that are 512 to 6656 in increments of 512. And we don't have to worry about like guessing by just using words and hoping and stuff like this. So we use the tokenizer. And then we run the benchmark, which is just a big old for loop. You gotta love a for loop. It's our double nested for loop even, right, where we have for our implementation in implementations, and then for length in sequence length. We're using TQDM to make it look pretty as best we can, and that's it. So you'll see here, first of all, just looking at the data, you can probably tell which is faster, just based on how long each run took. Right, so our naive sequences took us 1 minute 33 seconds to go through all 12 steps. and the FlashAttention-2 implementation took 28 seconds. So already we've kind of got a inkling that FlashAttention-2 is probably faster, but we don't know yet how much faster, how it looks. So we're going to go ahead and just graph her out. So load them into a data frame, graph out the data frame, and we get this beautiful chart, which shows us that indeed FlashAttention-2 is faster, especially at long sequences, right? So the growth curve of FlashAttention-2 is much smaller than the growth curve of naive implementation of attention. So that's just straight from transformers. And this is the crux of the FlashAttention paper, right? Which is that this memory complexity is it scales extremely hard in naive attention, and FlashAttention is meant to cut that. So it still does scale, and it still does get worse the longer we go with our sequences, but it grows a lot slower as we increase sequence length. So you can see here at our 6,000, we're considerably less than a naive implementation. And this is basically just, because we're doing less I/O. And because as we increase sequence length, we have to do quadratically more I/O operations with the attention mechanism. So this is ideal. We love to see it. Grows much slower than naive attention. However, if you zoom way in on this little dot here, right? I'll zoom way in. You'll notice FlashAttention actually takes a little bit longer, right? So a classic software engineering leak code problem style, right? This solution is more efficient the longer the sequence length is, and there is this crossover point. Now, very quickly, we eclipse it, even before we hit like 1024 tokens, which is kind of like a very short context length, right, for a model these days. FlashAttention is already pulling ahead. But the idea is that at that 512 mark, FlashAttention is actually marginally slower, right? And so this is the benefits. We only feel the benefits as we continue to scale the sequence length. But if you're doing something with a model that's only 512 tokens of context length, you have a very specific use case anyway. And so this is good to show us that, yes, it's faster. And then we can look at the numbers if you want to look at the numbers in the notebook. And that's it, right? So this is the kind of proof in the pudding, right? FlashAttention-2 is just faster, especially as we increase sequence lengths, right? It is better to use in all cases, except for if you have these extremely small generation windows or context lengths, which, again, most modern models don't have less than 4,000, let alone less than 1,000. And with that, I'll pass you guys back to Greg. But before I do, I'll remind you to like the video, ring the bell notification, subscribe. We're live every Wednesday at this time. We got some bangers coming up. So with that, I will actually pass you back to Greg.
Yeah, okay, so wait, hold on. Did you just say that it's actually not getting done in a flash all the time when we go to FlashAttention? You said that for very short sequence lengths. Is that what you said?
Yes.
So like you're just not feeding that many tokens into the LLM?
It's like our if our context window, right, is only 512 tokens. So this is the total combined input plus output. Then FlashAttention is marginally slower.
And why is that exactly? Just because? What's the intuition there?
You can think of it as there is some overhead added by FlashAttention, right? That is not yet useful or not yet adding performance enough at that small context length. Because remember, with FlashAttention, we have to like load these faraway memories. Like when we look at that beautiful diagram in their paper, we have like the green blocks that are loaded, and then they send things to the internal orange blocks, right? But the idea is that there is this amount of overhead that's created through this process, as well as keeping that running statistic, which is extremely effective and grows much slower, but it starts a little bit bigger. So this is like classic, leak code style DSA problem. It starts a little bit slower, but it grows, almost an order of magnitude slower as well. So it's the
Yeah.
moment we get past that break point, flash attention is like, I'm your guy.
Yeah, yeah. So it's kind of like you go and you want to build anything to scale out. It's like it takes more work up front to build
Yeah.
the scale version.
Yes,
Yeah,
exactly.
yeah. Okay, okay. Yeah, that makes sense. Okay, so yeah, we can just stay up here and throw your questions in the chat, everybody. Let's just sort of take a quick review here, Wiz. So flash attention 1, IO aware exact, reduces read writes between HBM and SRAM. Dope. Flash attention 2, starting to go deeper. We're not at the HBM SRAM level. We're now at the thread block and warp level, trying to exploit low occupancy or unnecessary, again, shared memory read writes. And then flash tension 3, Hopper GPU, get some. Okay. So then, in conclusion, we can kind of say this is really all about this memory bound issue. It's really all about this number of read writes. And we're constantly battling the fact that GPUs were just not built for this, especially as we go deeper and deeper and get bigger and bigger. So this tiling is the secret sauce to reducing the read writes between HBM and SRAM, exploiting those sort of, I'm not working that hard warps and thread blocks, while making sure that like we get sort of 100% utilization there is sort of what we're moving towards here. And really all this is, at the end of the day, like just use FA2, right? But maybe not for super, super tiny context windows. Okay. All right, great. All right. So, I'm sort of struck by like all this is really kind of about really, we talk about GPU utilization sometimes, and it's like, how do you get to like, as much utilization as possible? It really is just that simple. We're just trying to make sure that we're utilizing every little transistor on the freaking GPU. I mean, right? It's like, that's what all these things are driving towards.
Well, and that's exactly it. It's like, we know memory is a problem. We know it's a problem. So how can we minimize the problem, right? As much as possible by exploiting the architecture and exploiting how we can do the computations. Right? This is like something that we memed about a lot over the last 2 days, is this idea of in the shadow of the warp group,
That's
right?
right.
But what that really is talking about
Yeah.
is, while we're doing the next matrix multiplication, we can use those resources as well to start on the incremental softmax, right? So it's all about shoving that compute into as tight a space as possible, so that we can chew through that memory as fast as possible, so that we can use our slow memory to just barrage these smaller memory modules with information. And that's
Yeah.
the more we can remove these bottlenecks, right, the better things can be in terms of efficiency. And
Yeah. Okay.
yeah.
Okay, so we were kind of in the shadow of the GPU, and then the shadow of the processing cores, and then the shadow of the graphics processing clusters, and then the shadow of the streaming multiprocessors. Now we're in the shadow of the warps, and there's still some space there. And then maybe we'll get into the shadow of the CUDA, the CUDA chips themselves, and then like the shadow of the freaking transistors. It's like I guess we go all the way down. Super interesting stuff. If you guys like this GPU stuff, we're definitely interested in going deeper. And to that point, we're getting asked about going deeper here in the Slido here. Let's kick it off with this. They want to know about page detention, and of course, we don't have time to cover page detention, but it's what VLLM uses, right? Maybe it's time for a return to looking at VLLM in its more recent state in an upcoming event. But in short, how do you think about page detention versus flash attention?
I don't think they're really similar enough to have enough crossover to have like a meaningful discussion about it. But the idea is that page detention is just a way that we can think about partitioning attention. The actual computation of attention is still different. So
Okay.
Yeah.
Like we're making pages of,
yeah.
yeah, classic. Okay. Yeah. I think it is of interest to kind of go back and look at VLM and their updates. So maybe we will do that. Let's go to Nalay in the YouTube chat here. Why were IIRC the standard deviation time?
So yeah.
What's the question here?
Okay, so they're asking why were the standard? So if I remember correctly, IIRC, the standard deviation times like for like. So the idea being, why was the standard deviation time slightly higher for flash attention versus naive? They're I only run 10 trials, so I don't think it's super meaningful. Inference is actually quite consistent, especially if you're in a consistent environment. Something like Colab is pretty good for this. We had one spike that was likely due to just some some hiccup. Maybe memory loading was taking too long. Maybe the disk read got interrupted or failed. But the idea is that, when we look at the standard deviation and we only run 10 trials, it's really hard to say anything meaningful other than,
And who knows what kind of GPUs we have on Colab, right? I mean, like
A140 gig, but we don't know if it's a good one
the
or not
quality.
a good one. We don't, the hardware lottery is real, but the real intuition is that not enough trials, and we should expect the standard deviations to be quite low for inference, since there's not a ton of variability in the inference calculation.
Okay, we got a classic question coming in. Actually, let's end on the classic, and let's go to another quick question on VLM. Is VLM a serving solution, including things like batching requests, while flash attention is specific to computation?
100% true. Yes. So VLM is a whole inference optimization platform, if you want to call it that. But it is a inference solution, a serving solution. It is the thing by which we load models and then serve tokens for models. Flash attention makes attention go really fast. So there's not a ton of overlap here. Like Flash attention is not trying to serve your model. Flash attention is trying to improve something that's internal to the model, right? So one's kind of meant to be the whole thing, and one's just meant to be like, it's a difference between a whole car, right, and someone just souping up the engine.
Yeah,
soup up the whole car versus the whole engine. There's different components there. So
okay,
yes, great question. Great question.
Yeah, I like that. Okay, last question. This is the classic banger for all the GPU noobs and the GPU poor out there. What GPU do you recommend for home PCs that might profit from this kind of flash attention? Affordable.
All of them. As long as you're over 512 tokens. RTX 4090 is probably your best bet for consumer chip. If you got the cash, Ada A6000 will also go burr. But the idea is that you can even use a 3090. So this was done with Ampere. Flash attention was done on the Ampere architecture, so you do have to make sure you have an Ampere chip. Other than that, Ampere and forward. Other than that, I would say like 4090 is probably your best bet these days. It's got like 24 gigs, so you can fit in, 3.5 mini instruct with, a sequence length of 4096, and at 4096, FA2 is much faster than naive. So.
And when you say it's got 24 gigs, you mean 24 gigs of SRAM just attached to the chip?
24 gigs of HBM.
HBM, baby. Okay, all right.
Much smaller cache. Much smaller cache. Yeah,
all right. Awesome, Wiz. Thanks for walking us through that today. And that's Flash Attention, everybody. We'll see you next week, Wiz. And it's time to go ahead and wrap. Thank you for joining us for Flash Attention 2, next level attention. We think it's pretty next level, and we think you as builders should go out and start building, shipping, and sharing with it today. If you do build, ship, and share something with FA2, smash the Discord. There's a build, ship, share channel, And we love to highlight folks that are building awesome stuff in our newsletter each week, as well as repost anything that you tag us in on LinkedIn or X. So join the community and start building, shipping, and sharing today if you're not already on the path. And if you're interested in accelerating your education and your understanding of technologies like FlashAttention-2 and how to build production LLM applications, check out our upcoming course, the AI Engineering Bootcamp, that will get you on the path to really achieving your goals in 2025 in generative AI. And hopefully connecting with some really awesome members of the upcoming cohort. We'll kick off on January 14th for cohort 5, and it's shaping up to be the best yet. We had at least 2 startups come out of the last cohort that are raising funding today. It's really just an amazing time to be in the space. So thanks for joining us on YouTube today, everybody. Keep building, shipping, and sharing. In the meantime, we will do the same, and we'll see you back next Wednesday, where we're going to be talking on-prem RAG, agentic RAG, to stay in buzzword compliance with Llama Index. We'll see you guys then. Have a great week, everybody.